start, are there any questions from the things that you've been going over the last couple of days before we look at equations of planes? In the chat so I can see it, just in case you type something rather than write it, say it. Okay, so all right, that's cool. Hoping you can see this my OneNote screen. Let me know if you can't. So we've been looking. So we're looking at vector products and its usefulnesses. Usefulnesses, that's not even a word. So we looked at the idea that if we find the vector cross product, then that provides us with the normal. So a vector perpendicular to the plane that those two vectors are on, and that also has applications in finding areas. And we could actually find the vector triple product, scalar triple product, which includes a dot product and a cross product together to find volume. So just as a by the by, let me just pull this in. So some of the concepts that we are talking about. Goodness me, my computer's a bit slow today. So if we look at our on our formula sheet, okay, so we can see that we've got some formulas that we've been discussing. The vector, the scalar triple product is not on here, as neither is the area formula. So both of those are sort of applications of the vector cross product that you can see in the middle of the screen here. So we've got the AB sine theta version with the n hat, which is the unit vector in the direction of the perpendicular. It's the num. So and then we've also got the actual. Whoops, you actually got the actual cross product itself, written in a slightly different form to what we've been using, the IJK, but it's the same calculation that we've been doing. So I just find that the version that I've given you seems to be a little easier to work with. Today, what we're going to be moving on with, unless you have some questions, and silence is what I've got so far. So I'm assuming that that means that you must be okay with that work. Is that a reasonable assumption?
Yeah, that's fine.
Yeah. Josh, yeah. Yeah. Josh? Cool. Okay. Thank you for that. No, I appreciate the thumbs up. All good. Either way. So, all right. So what we'll do then is I'll leave those there. We've got some time in our lesson on Friday where I'm going to just give you time to solve, work on problems and so forth. So if you do come across something, please don't hesitate to ask on Friday or before if you need to. So what we're going to focus on today is something that comes up in the exam, both in your Unit 3 exam at the end of this term, but also it has been on every external exam so far, everything has been to, but is this idea of equations of planes and how you could derive the equation of a plane given different scenarios. And so we've looked at equations of all sorts of different surfaces in one dimension. So we can see we've done hyperbolas and we've done ellipses and we've done circles and we've done lines and we've done parabolas and et cetera, et cetera, et cetera. But what we haven't really talked about is describing three-dimensional surfaces. And so I've got the notes that I've taken actually out of the Cambridge textbook, but I want to expand on them and because there's a lot of things in these notes that are there for you to read that assume that you can take it from one step to the next without any explanation. And it's possible that you can, but I think it's important that I'm going to go through this in a fair bit of detail, because if you have an understanding of where the equations come from, so for example, if you look at this equation here, actually I'll do it down this way. So these are the two equations that we end up with, whether it be a vector form or Cartesian form, and you look at it and you go, well, what the heck does that even mean? So I want to take some time today to go through the derivation of both of those formulas. And it also helps us, also reminds us about some of the concepts that we've already covered last term, end of last year and before, prior to that, so that we can bring all that together into this area. And this is one of the last things that we actually have to do in vectors in this section of vectors. So that'll be good. All right, so I'm confident that all three of you, and please correct me if I'm wrong, so speak up if this is not correct. I'm confident that you all have the concept of what a plane is, okay? So basically imagine a piece of paper that you're sort of holding up, and that piece of paper can be in any direction, in all three dimensions. Okay, and that effectively is a surface that we're considering. Okay, so pardon me, it's in 2 dimensions. Okay, now it's a 2-dimensional surface in a 3-dimensional space. Okay, so it has length, depth, but it doesn't have. It has length and width, but not depth. But its position is in 3-dimensional space. So it's a bit of a to get our head around. So you can see on your screen there's a couple of diagrams of that. And so in order for us to define a particular plane, we need 2 pieces of information. The first thing we need a fixed point on the plane. Okay, so we can identify a fixed point on the plane, and then we can identify a perpendicular vector to that point or to the plane. It doesn't have to be at the point. It can be anywhere on the plane, but for the ease of argument, we tend to put it on the actual point just to help us with our understanding and also with the calculation. So hopefully you can see, and I'm going to zoom in a little bit. So this is the diagram that we're going to be working with. So the fixed point that we're going to focus on is this point A. Okay, so the point A will have a set of components, yeah, A1, A2, and A3. So let's just consider them to be those points there, all right? We could also call them A, B, C. It doesn't really matter what we call them, okay, or what the definition is, but they're a fixed point. So that's a point in space. So it might be -2, 2, 5, or whatever, okay? We've got our origin down here, okay? And so if we want to define the position vector from the origin to that point in space, then we call it little a, as we're accustomed to do, okay? Now, what we need to do is identify, well, if we want to define a plane, then we're going to need we need a bit more information. So what we're going to do is we're going to define any other point on the plane. So we're going to call it point P, and it has a point X, Y, and Z. Now, if you recall, all right, if we want to define an equation of a line, okay, the equation of a line, let's just use 2 dimensions for a start. The equation of a line has X and Y in it, okay? So they have a general point that falls on the line, okay? And then X and Y, so we've got that Y equals the typical version for a line, right? We have Y and X, and the M and the C are the bits of that equation that are specific to that line. So it's the grain of a line and the y-intercept for a line. So we have a similar idea when we define a plane. Okay, so we have fixed information. Okay, so the fixed information is the point, and we have a perpendicular vector, which we call n. Okay, but we need, in order to come up with an equation, we need some sort of variables in there so that we can then substitute points in and do some stuff with it. And that's what the X, Y, and Z are. So we've got this point P, X, Y, Z, which is it can be any point on the plane. So that's defined to be. Just like in our line equation, X and Y are any point on the line. Okay? If at any point in time during this you get stuck or you're not sure, put your hand up and say, "Hoi, can you just go through that again or re-explain it," or something like that. So if you get lost, please don't let me keep going without you telling me. Okay, so far we've got a point on the plane that is fixed, and we've got a general point on the plane, which is P. Okay, and so by definition, instead of calling this little p, for whatever reason, mathematicians have decided that the position vector of this general point P is going to be given the symbol r. Okay, and so you will have noticed if you remember that in the general definition of a vector equation, there was an r in it, and that's where the r comes from. So the general form of a vector of a plane in vector form is this. The first thing to know is, what the heck is all that? Okay, so now if you look at those, you can see, well, that's the position vector of our general point. N is the vector form of the normal, and A is the position vector of the fixed point, and then we've got N again. So what we're going to look at today is, well, where does that formula come from? How do we get to that? What does it look like, and how do we use it? Okay, so let's talk about how we might define that. So first thing we're going to do is, if we've defined a fixed point and a general point, then let's talk about that point there, AP, that vector AP. Now, using vector subtraction in this case, okay, if I want to go from A to P, then I've got to go down A, and then up to R. So that's negative A plus R to get to P, which is another way of saying R minus A. Okay, so that's a piece of information. So we've got a vector that's on the plane. So AP is on the plane because both A and P are on the plane. So therefore, AP is a vector on the plane. Okay. Second piece of information that we know is that the N, the normal, is perpendicular to the plane. Okay. So if I have a vector perpendicular to the plane and I have a vector on the plane, so I've got two vectors that are perpendicular to each other, what sort of mathematical relationship do we know about two vectors that are perpendicular? Can you recall?
Don't they multiply together to equal 0 with the...
Yeah, don't say multiply. Yeah, so sorry, I cut you off.
No, never mind. I think I
No. So instead of saying multiply, you're on the right track, but it's not multiply, it's what?
Dot product.
Dot product, exactly. Yeah. So the dot product of those two vectors is equal to 0. So that's something that we know, right? So therefore, if I find the dot product, of AP and this known perpendicular vector, then I know that's equal to 0. Okay, because they're perpendicular by definition. So we know that AP is R minus A, right? Dot N equals 0. And if I use my understanding of dot product and there's the associative law, not the associative law, distributive law, my apologies, the distributive law, then it's going to be R dot N minus A dot N equals 0. Okay, so basically I'm just expanding it out, just like you would with multiplication, but the dot product works exactly the same way, has the same properties. Therefore, I can then rearrange that. R dot N equals A dot N. And that's how the vector equation comes about. Okay, now what you have to remember is that R is X, Y, and Z. Okay, and so what we're going to look at, therefore that's how we end up with our vector equation. So that's our vector equation of a plane. So what we're going to do before we go any further is what we're going to look at, well, how do we use that? What big deal? What does that mean? So let's have a look at a quick example, okay? And then we're going to come back and say, well, how do we convert that to a Cartesian form? So let's have a look at an example. So for a plane, plane 2, so it's a two-dimensional plane, okay, in a three-dimensional space. That's what the little 2 means, all right? It's a Roman numeral 2. Talks about talking about two-dimensional, okay? Sometimes they write plane, but they don't write the 2. Just be aware, okay? The vector negative I plus 5j minus 3k is normal to the plane. Okay, well, if that's the case, then that's n. Okay, 5j minus 3k. So we're told, whoops, that's our normal. Okay, so that's n. And the point A with position vector that is on the plane. So there's a given point on the plane. Okay, so that's my A. Because if it has a position vector, so the point A has a position vector of this, minus 3i plus 4j plus 6k. Okay, so there we have our two pieces of information. Find a vector equation. So we're just going to do the first part, the vector equation part of it first, okay, and then we'll deal with the Cartesian part of it in a second. Please excuse me. Okay, so just to remind you, okay, that you can see here on your formula sheet that this formula is given to you. Okay, vector equation of a plane R dot n equals A dot n. So your responsibility is to remember what the variables mean. So what is the R, what is the n, and what is the A? Okay, so you need to learn that, but once you got that, and I've got it obviously on the screen as well, but I just wanted to show you that it's a formula you don't have to remember, but it's important that you know where it is and how to use it. Okay, so can someone remind me, what is R? Because it's the only thing I haven't written on the screen. So I've got N and A, what's R?
Isn't R just another point on the plane?
Yeah, bit more information. It's slightly more, I mean, just to be a little bit more pedantic, what about, what point on the plane?
A point that is perpendicular to the normal?
Yeah, it's any point. So it's the position vector of any point on the plane. So it's a general point on the plane. We just want to make it a bit more specific because A is a point on the plane, right? So R is the position, or A is the position vector of a point on the plane. R is the position vector of any other point. So an infinite number of other points on the plane. Okay, so it's like the X and the Y in a line equation. So we're going to leave R as it is, okay? Because R effectively is xi plus yj plus, pardon me, zk. Okay, so just keep that in mind. All right, so we'll come back to that shortly. All right, so let's leave it as R dot n. So n is negative 1i plus 5j minus 3k. Okay, so that's my R dot n equals, okay, well, A dot n, well, that's just dot product. So let's do that. So A dot n is going to be negative 3 multiplied by negative 1 plus 4 multiplied by 5 plus, come on, slide over. By the way, this is the work solution of this problem and other problems over here for later on. And I've got 6 multiplied by negative 3. So that's going to be 3 plus 20 minus 18. So that's 5. 5 equals 5. And that is my vector equation of that plane. Okay, big deal. Does it tell me much? It tells me a bit, and we'll look at some examples shortly about what it actually means and all that sort of stuff. But that's it. So if it asks you for the vector equation of the plane, there's your answer. Okay? Pardon me. All right, so, okay, that's fine. That's the vector equation of a plane. So we've got R is the position vector of any point on the plane. If I find the dot product of the normal, then the answer is going to equal 5. And so that's my equation. Okay? So let's go back to this and go, okay, well, okay, that's fine. All right, but how do we then create the Cartesian equation? Okay, so let's deal with that. All right, so let's solve that problem. So if we go back over to here, all right, so we've got R dot n. So I know that, pardon me, pardon me. All right, so let's sort out, let's go back up to, what do I want to do here? Yeah, I want to go back to this equation here. We go back to this equation here. Okay, so let's go back to that and let's see if we can sort out what our Cartesian equation is going to be. So what we're going to do is we're going to rewrite what you see in the blue circle in Cartesian form. Okay, so let's define R as being, all right, any point on the plane. So let's put that back in, y, j plus z. Okay. Okay. And we're going to define our point, any point on the curve. Now I'm just going to make, we can call anyone we like, A1i plus A2j plus A3. Okay. Okay. All right, so all I've done is just defined, so instead of talking about it in terms of vectors, we're going to talk about it in terms of Cartesian. And so we've got, like if you like, this is the vector side of the equation, this is the Cartesian side of the equation. So we're going to combine them together. And we already know that n, okay, n is some vector that is perpendicular, so n1 plus n2j plus n3. Okay. Okay, so a very general form. I'll show you this in a specific example in a minute. Okay, that we just did. So how it will look in this example, but we'll just do this generally first. Okay, so what we're going to do now is we're going to apply the blue circled equation with our Cartesian information. So it's going to get quite long, but it drops out nicely, and you'll see what I mean by that in a second. Okay, so just bear with me for a moment. So R minus A dot n equals 0. Okay, so let's do the R minus A first. So R minus A is going to be x minus a1 I plus y minus a2 j plus z minus a3 k. By the way, you do not have to reproduce this in any time in your exams. I'm going through it in this amount of detail because I think if you understand where the equations come from, it makes applying them a little bit easier. Okay, so please bear with me because this will take a few lines to finish. All right, so there's my r minus a dot n. So n is n1i plus n2j plus n3k. Okay, and that equals 0. So I'll just maximize this so we've got some space. Okay, so there we are there. Okay, so now we're going to dot product this. Looks nasty, please excuse me, but it's not too bad. So remember with dot product, we just collect the I terms together, multiply them together. So it's going to be x minus a1 times n1 plus y minus a2 times n2 plus z minus a3 times n3 equals 0. Okay, big deal. So I'm going to expand out the brackets. Okay, so I'm going to have n1x plus, oh, sorry, my mistake, minus a1n1. All right, I've written in this order for a reason. So n2y minus a2n2 plus n3z minus n3 a3 n3 equals 0. Okay, looking a bit long and involved, but if you think about what we're trying to achieve, we're trying to write a formula in Cartesian form. So a formula in Cartesian form has x, y, and z, in this case because it's three-dimensional, x, y, and z in it. So I want to come up with an equation with x, y, and z, and so we're going to put all the x, y's, and z's on one side of the equation, and we're going to put all the non-x, y, and z, so all the constants, on the other. Okay, so if I do that, n1x plus n2y plus n3z, right, equals a1n1 plus a2n2 plus a3n3. All right. Can anyone, so let's have a look at what we've got here. Can anyone tell me what that is equivalent to? A1n1 plus A2n2 plus A3n3. What is that equivalent to? Or what's a shorter and quicker way that I could write that? It's going to minimize something.
A dot n.
Very good, Mason. Yep, exactly. It's A dot n. That's exactly right. Okay, which hopefully you can see is that. Right? Now, I'm going to leave that as A dot n because it's just quicker and easier. And I'm just going to write this now. Now, I'm not going to simplify this side because it defeats the purpose of what I'm trying to achieve. But what can you tell me about N1, N2, and N3? What are they? Where'd they come from?
The n vector?
Yeah, and which is what? In terms of the plane, what's the n vector?
A general point on the plane.
No, that's P. That's
no.
R.
Yeah, that's the normal.
Yeah, it's the normal, exactly. So to define the Cartesian equation of a plane, well, we need the normal. So the coefficients of our x, y, and z are just the normal. Pardon me. And what it's equal to is the A dot n part. So a point and the normal. And that's where, if you look over here, okay, there's my Cartesian equation. N1, N2, N3, right, are the coefficients or the points that define the normal, okay? And then we've got our K, which is A dot n. Okay, so let's go back to the example that we were working on, which is this one here. So that's my vector form. That's it there. Okay, if I want Cartesian form, so I'll just do a different highlight color just so we can see where we're at. So I'm going to do Cartesian form. Right, so Cartesian form is n1 x plus n2 y plus n3 z equals A dot n. So what would that look like? So n1 is what?
-1.
-1. So it's going to be negative x plus 5y minus 3z equals, and we've already done A dot n, we did it earlier, 5. And so that, gentlemen, is my Cartesian equation for the plane defined by those two pieces of information up there. And so we can see that negative x plus 5y minus 3z equals a number. It's sort of more like an equation that we are comfortable with. We've been working with Cartesian equations since grade 9. Okay, when you were first introduced to y equals mx plus c, okay, that was your very first Cartesian equation of anything. All right, and so y equals, so, and what I introduced to you guys probably last year, you might have got it in grade 10, is the general form of a line. Okay, so the general form of a line is ax plus by plus c equals 0. So if I just reorganize that, okay, it's in the form that we're familiar with, a coefficient of x, a coefficient of y, because it's a line's only got x and y components, it doesn't have a z part, okay, equals a constant, okay, and I could make that positive c, it doesn't really make any difference, right? That's what we're comfortable with doing. Okay, so negative x plus 5y minus 3z, okay, that sort of feels like a Cartesian equation that I can deal with. And it's really easy to find. As long as you know what the normal is and you've got a point on the line, to get the 5, you just dot product the point and the normal. That gives you your constant, okay? And then the coefficients of your normal are the coefficients of your x, y, and z for your Cartesian form. And so that's how we define a plane, either in vector form, it's highlighted in blue, or in Cartesian form, that's highlighted in yellow. Okay, now, again, on your formula sheet, you'll notice that the Cartesian form is given in a slightly different way, A, B, C, and D, which I think they've done it that way because there's no hard and fast rule of how you define what the normal vector is. So we've called normal vector n1, n2, n3 for hopefully obvious reasons. So they've come up with that form. But what you have to try and remember is that the A, B, and the C, okay, are the coefficients of the normal, and the D has been derived from the A dot n. Now, it's obviously moved to the other side of the equation, so it's slightly different to what we're used to, but hopefully that's going to be not too difficult for you to recall. So before we go, so that's that example there. Before we go any further, are there any questions on that? Does that make sense so far?
Is it fine to leave it in the vector equation format with the R there?
Yep, that's what you would do. The vector form would have the R there. So if you look at, again, I'll pull up the formula sheet. You'll notice it's got R. So R is your position vector of any point on the plane. And so because it's any point, you don't actually, it's not defined in like specifically. So there's no A, B, and C value. There's no coordinate. It's X, Y, and Z. So to find your vector form of your plane, you have to have the R as a vector. That defines it to be vector form. You can write that, all right? So you may see it written sometimes as R dot -1, 5, -3, and that could also be written as a column vector. Doesn't have to be a row, it could be a column, okay? Equals 5. All right, so again, just pulling this up. See, you'll notice here the vector cross product, they've got the vectors written as column vectors, A1, B, A1, A2, A3, etc. They're written as columns, okay? You may sometimes see the normal vector written as a column vector as well, but it's the same outcome, okay? All right, so that example that we just worked through here would be a simple familiar type question, okay? So let's have a look at one that's a little bit more difficult, but it'll help us, it'll remind us about a concept or topics that we covered at the end of last year. So I'm sort of doing this only because I wanted to remind ourselves about how to actually do this part. Okay, so this would be a complex familiar. So if you're given this question on your exam, this would be complex familiar because it involves multiple steps. But it's all steps that we need to be able to do. Okay, so let's work our way through this. So I'll give you a chance to have a quick look at it first. Okay, so find a vector equation and a Cartesian equation of the plane contain the lines R1 and R2. Okay, so those are two lines on a plane. Okay, so we're not given, so in order to define a plane, we need two things. We need a point and we need a normal. And at the moment, we don't have either of those things. Okay, so if you've given two lines on a plane, okay, if the lines are parallel, we're buggered. Okay, because we can't find a point on the plane. All right, so what we need to do is hope, and it's almost a guarantee in our level, that the lines cross. And if we can find where the lines cross, then we've got a point on the plane. And that's what we need to define it. So challenge number one, find where those lines intersect. Now, do you remember how to do that? So what I want you to do is, if you do remember how to do that, give me a thumbs up. If you don't remember how to do that, don't. I got nothing. Okay, that's all right. Okay, so this is good revision, okay, because, yeah, I was laughing too. All right, so this is good revision. So we may not get through this whole example before the end of the lesson, but that's okay, because the second and third parts of this example are what we've covered in the last couple of days. So the second part of it will be finding a vector cross product, okay, because of the point, and I'll explain how we do that before you disappear. And then the third part is to do what we just did, which is once you know what the normal is and you've got a point, you can then find the vector and Cartesian equations. Okay, so first thing to do, where do these points meet? Okay, so the first thing we're going to do is we need to identify the point where they meet. So how do we do that? We need to find the values for lambda and mu. Okay, so you'll notice that these are given in parametric form. So there are two lines on a three-dimensional space given in parametric form. So what we need to do is we need to organize this into Cartesian form. All right, so the first job is rearrange R1 and R2 into Cartesian form. So the way that we do that is we collect all our i's together, all our j's together, and all our k's together for each of the two lines separately. Okay, so you'll notice that if I'll do the first one, and then I'll give you 60 seconds to do the second one. So in the first one, I'll just do it in blue. So there's I, and then we got, so if I expand out the brackets, I'm going to have 5i plus 2j. Now there's no k, but that's okay. So 5i plus 2j plus 2 lambda I plus lambda j plus lambda k. So if I was to collect all the I terms together, I'd have 5 plus 2 lambda I plus 2j and then lambda j, so it'll be 2 plus lambda j plus, now I've got no k outside, but I've got a lambda, so I've got one lambda, so lambda k. Okay, so that's me changing it from parametric form into Cartesian form. Yes, there's still a parameter in it, and we'll deal with that in a second, right? But that's how we do that. So very quickly, can you do R2? So do exactly the same thing for R2. So I end up with that. Again, don't want to rush you, but hopefully that has, you do agree. So do you agree with what I've got? Just a thumbs up or an unmute and say, yeah, whatever. Or if I've made a mistake, let me know. Yep. Cool, thank you. All right, so let's go. So now, so we've done this, pardon me. So we've organized these into Cartesian form. Good, thanks, Josh. So the next step is to say, rightio, they're in Cartesian form, but I need to know where they cross, right? So they're going to cross at a particular point in space, or we hope they do, particular point in space. So what we need to do is we need to find what value of lambda for line 1 and what value for mu in line 2 will make that point equal. So what I want basically is I want this part to equal this part so that the I component is the same point in space, right? I want the J's to be equal and I want the K's to be equal. So if those three components are all equal to each other, the I's are equal, the J's are equal, and the K's are equal, that must be the same point in space. So effectively what I've got is 5 plus 2 lambda has to equal minus 3 plus mu. Okay, and 2 plus lambda has to equal 4 minus mu, and 6 lambda has to equal 6 minus 2 mu. Okay, they have to equal each other. Otherwise, if they don't, like even if these, the I's are equal and the J's are equal, but the K's aren't, they're not going to cross at that point. Okay, they're going to be parallel to each other most likely. Yeah, well, they could be parallel to each other or something else, parallel, I think. So what we need to do then is go, okay, we need to solve for lambda and hope that we get the same point when we have lambda and mu. So let's see what we do. So if we're going to solve these, okay, so I'm going to rearrange them into equations and then we're going to solve them. So I've got, pardon me, so I've got, I already know that lambda is 6 minus 2 mu, so I'm going to use that concept. So I'm going to call that one equation 1, for want of a better way to put it, and I'm going to substitute it into here. Okay, so I'm going to have 2 plus 6 minus 2 mu equals 4 minus mu. Okay, so the beauty of this is already got, it's rearranged and I can substitute it in. So that's got 8 minus 4 is 4 equals minus plus 1 is mu. So mu is 4. Okay, I'm not going to go through how I got that. If I made a mistake, hopefully I didn't, but if I did, you can tell me later. Therefore, lambda is going to equal 6 minus 8, which is -2. So that's my values for, and I can check that by substituting them into each equation and see if it works. So 5 minus 4 is 1. -3 plus 4, 1. Okay, so it works in the first equation as well. So then what I do is say, well, what's R1 then? So R1 to do with lambdas. So lambda is -2. So 5 minus 4 is 1. So that's going to be I. 2 minus 2 is 0. So plus 0J. So I'll just put that there. And then I've got, plus -2K. So minus 2K. Yeah, minus 2K. Okay, so just double check that. 5 minus 4, 2 plus -2. Yeah, okay, right. So R2 is going to be, so this is now mu, so be careful here. So -3 plus 4 is 1, so I, beauty. 4 minus 4 is 0, awesome. I'm going to write it in just for the purity. Obviously don't need to normally. And then 6 minus 2 times 4 is 8, so that's -2K. And you'll notice, not obviously, but it's what we want. The 2 points are exactly the same point. So the points on the line is, so therefore my point that I want, so therefore my A, right? My A, which is a point on the plane, is 1, 0, -2. And so that's equal to my A. Are we okay so far? Yep. Okay. Cool. That's step 1. Okay. Step 2 is a concept that you're going to have to try and remember from when we talked about this in the early part of this unit, which is obviously last term. Now, if we want to define a vector, we need two pieces of information. Sorry, the vector equation of a plane. We need two pieces of information. We need a point, which we've got now. Tick. Okay. We need the normal. Okay. So we need to find the normal to this plane. Okay. So there's my point. The next step is the normal. So how do we typically find the normal? We use a cross product. Okay. So I have two lines, right? I have two lines on the plane. So I've got two bits of information that if I find the cross product of those, I'll end up with a normal. Okay, so if we go back to my equation, okay, there's my equation for one line, my equation for two lines. Now, the beauty about the way this is set out is that I only need to use, in order for me to find my equation of the line, I'll use the green, sorry, to find the normal, I only actually need that bit and that bit. All right. Now, if we think about those, if you recall from our definition of a line, now I probably won't be able to find this quickly, but I'll see. Oh, yeah, vector equations of lines. Here we go. Beauty. All right. If you recall, oh, shush, sorry, my phone's ringing. Let me just turn it off. Okay. So if you recall from our vector equation of a line, okay, then we've got our vector, so R is equal to a point, A, plus some parameter times D. Okay. Now, D is the unit vector in the direction of the line. Okay. So D is the direction that the line is traveling in. Now, if we go back to the question we're currently doing, I can just find it. Right, that one, it's this one, right? These lines are in the same form. Okay. It's got a point, in the first case, it's 5i plus 2j. So that's a point in space. There's no k component, so it's on the k-axis, right? Oh, sorry. There's no k component. I shouldn't say it's on the k-axis. My apologies. Right? Plus lambda, which is some parameter, multiplied by the direction. So the 2i plus j plus k is just the direction that that line is traveling in. Similarly for R2, it's a point plus a parameter times the direction the line is in. So if I want to find the normal to those two lines, the only bits of information I need are the bits that tell me the direction. I don't care where they start, that's irrelevant. I just need to know the direction they're going in so that I can then find the normal. So when I do my cross product, which is what I need to do now, oh, that's a bit dumb, I can't see what the lines are now. So tiny, all right? So all I need to do is cross product 2i plus j plus k crossed with I minus j minus 2k. I minus j minus 2k. Did I remember that correctly? Yep, okay. And so that's all I need to use. I don't need the first part of it to find the normal. I just need the directions they're going in because that's the vector component part of it. And I just use that. Okay, so we're about out of time. So here's what I'd like you to try and do. You know how to find that cross product. We've done it. You've done it a few times now. I, j, k, right? Bang, 2, 1, 1, negative 1, negative 1. Oh, sorry, negative 1, positive 1, 1, negative 2. Right? So this is going to be your n. Okay, so I want you to find n. Won't take you very long. And all right, so I want you to do that. So then you've got your a and you've got your n. So from that point on, you can then find vector form. Dot n equals a dot n. Cartesian form. Okay, so I'm going to write it as we've learned it, n1 plus n, whoopsie, n2y plus n3z equals a dot n. Okay, so that's what I'd like you to try and finish off. Okay, now just before you go, I just want to show you, now to follow up on this, so you've all joined the class yesterday in Jack. So when you go to your dashboard, okay, what you will see is class assignment. So basically a class assignment is where I've set you some questions to do. Okay, so just flick back to your OneNote for a minute. So they're these questions here. So if you want to work through the exercise from the textbook, you can do that. And they're the questions there, 1, 2, 4, 6, 9. But I've set them up in Jack so that you can go in and have a go at it. So I'll just show you what it will look like when you go in. So I'll just change to student for reasons. So you'll see this, okay? So you go to answer questions. Takes a bit to load. My internet today is particularly slow, much to the disgust of my family. All right, so it comes up looking like this. Okay, so I just want to, pardon me, show you what you see. So this is question number 1. It's still sort of loading, I think. Oh, it's not too bad. You can open up a whiteboard. So if you want to like use your finger and whoops. Free drawing tool, so you can actually just write there if you want to. I'm not sure if your laptops are touch sensitive or not. Don't worry about the timer, it just starts timing you. That's good for your own information, it doesn't record it at all. You can pause it if you want. If you want to get out of the task, you can. And there's some questions there. So you can see that you can type in your answer. Once you've typed an answer in, and it comes up with a calculator if you wish to, or to type it in if you want. Once you've typed your answer, you can submit it. Once you've submitted it, you can see the work solution. Okay, and so you can see, it'll tell you if you're right or wrong, and you can see the work solution. Okay, you can navigate your way around the questions any way you like. If you find that you're on question 2, you think, oh man, I'm stuck, I don't know how to do it. You can flag it for yourself, all right, and you'll see it comes up like that. So if I move to question 2, it's flagged, all right, and then it'll tell you later. It doesn't tell me, but it'll remind you that on Friday when we're next together, you can say, oh, sir, by the way, I had trouble with question 2, for argument's sake. All right, and so you can work your way through those. You don't have to do it in here, but it does mark it for you, and it shows you the work solutions if you're not sure. When you're done, you can finish and submit all, and then that shows, and then I'll see where you're at. Now, the beauty about me seeing is that I'll see where you were, what you could do and what you couldn't, so that I know where to focus any remedial stuff. So if I need to go back and say, oh, we didn't quite understand that concept, then I can cover that for you. All right, so you've got that option there. If you don't want to use that option, you don't have to. I'm not saying you do. I just recommend that you do because you've got access to the solutions and all that sort of stuff. All right, so again, that's from your dashboard. You can see that from in here. So this is what your dashboard will look like because it's in student mode at the moment. Okay, I've held you up over time. I apologise for that. Not unusual, is it? Does anyone have any last minute questions before I head off?